Alrighty, here we go with Chapter 8, last chapter in the book. We're looking at fundamental counting principle. And right off the bat, I'm going to put a plug in for the funniest math counting video that I think I've ever seen. And that's coming out of Board Shorts TV. Check it out. Highly recommend it. Now we're going to do some tossing of coins and spinning of spinners. Fun stuff. Let's list all the possible outcomes if we do both of those. Here's a keyword, and we're doing both of them. So if we look at what we've got, I've now got from the coin, maybe heads for H. Let's say T for tails. Let's use S for shaded. And let's use W for white. And let's bring them all together. What are all the possible outcomes we've got going here? We can have heads and then shaded. I could have heads and then white. I could have tails and shaded, tails and white. So there are 4 outcomes. And then just what's the probability of each one of those happening? Well, this is 1 out of 4. And every one of them is equally likely, 1/4 probability, or 0.25, 25%. All right, for all you musicians out there, trumpet playing. 3 different valves, they're sitting right here. You push them down. What are the possible orders that we could have them? Lots of ways of being able to go through this kind of a question. You could make a full table and say valve 1 and all the possibilities, valve 2. I recommend not using a chart. I recommend going back to your tree diagrams. Let's remind you of what those look like. We've got valve 1, valve 2, and valve 3. There, spread it out a bit. Okay, in valve 1, you've got 2 options. It's either down or it's up. Spread those out. If the first one's down, now we go to the second one, and it's either down or it's up. But if the first one was up, then the second one is either down or up. And now we go to the third valve. If the first one is down, the second one is down, the third one could either be down or up. The first one's down, the second one's up, the third one's either down or up. And you continue that. First one's down, first one's up, second one's down, then it's either down or up. First one up, second one up, down and up. And now we list all of our possible outcomes. Down, down, down. Down, down, up. Down, up, down. Down, up, 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 down, down, up, down, up. Sounds like we're dancing here. Up, up, down, and up, up, up. And count them, 1, 2, 3, 4, 5, 6, 7, 8 of them. There are 8 possible outcomes. All right, let's get right into example number 1 there. Fan has 3 settings, off, low, high. How many ways are there to set 3 fans? Well, we're going to do it exactly the same way. Fan 1, fan 2, fan 3. Leave lots of space for this one. First one, it's either off, low, or high. Spread them out when you're doing a tree diagram. The second fan is either off, low, or high. Off, low, high. Off, low, high. And the third fan, same options. Off, low, high. Off, low, high. Off, low, high. Oh, I hate this. Off, low, high. Off, low, high. Off, low, high. Off, low, high. Whew! Off, low, high. Off, low, oh, high. Oh my goodness. Let's list all of what we've got there. Or we just need to know how many. So let's just count the end. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18, 19, 20, 21, 25, 26, 27. Oh, there's got to be a better way than this. Now looking at their example, they did the same example as we just did with lamps. That example there illustrates what we call the fundamental counting principle. So if we look at that first lamp that they had, at off, low, medium, high, they had 4 options for that one. There's 4 ways to set that first lamp. For each of these, there are how many ways to set the second lamp? 4. And if you look at that answer, 4 ways for the first, 4 ways for the second, you got 16 in total. And that's telling you now we can multiply 4 times 4 gives us 16. Let's look at one we just did. There's 3 for the first, 3 for the second, 3 for the third fan, 3 times 3 times 3. Oh, 27. Look at that. That's a heck of a lot easier than counting them all out. So all we're doing in this saying in fundamental counting principle is just multiply the ways for each of the different steps, for each of the different objects. And we take it through as many as we have. We don't just need to have 3. We can have however many. All right, let's see what you can do. You got 3 pairs of pants, 4 shirts. How many different ways can you dress for the day? And we're assuming that everything matches, you know, we're all stylish. Hey, check it out on your bit.ly link there. Now looking at their example 2, I think is a good starting point, and I'll let the guy here explain it to you.
From 2010, Alberta assigns license plates with 7 characters, A, B, C, 1, 2, 3, 4, replacing the old 6-character plates A, B, C, 1, 2, 3. All 26 letters A to Z and 10 digits 0 to 9 may be used more than once. Part A. How many license plates were possible with the old plate? I'm going to use the fundamental counting principle. There were 6 characters on the old license plate. The first 3 characters were letters, and for each letter, there were 26 choices. The last 3 characters were numbers, and for each number, there were 10 choices. I can multiply to determine the total number of possible plates. 26 times 26 times 26 times 10 times 10 times 10 is 17,576,000. So, 17,576,000 license plates were possible with the old plates. Part B. How many license plates are possible with the new plate? The new plate has 7 characters. The first 3 characters are letters, and the last 4 characters are numbers. I already know that the product of these first 6 numbers is 17,576,000. So I'll just multiply that by 10 to get the total product. So 175,760,000 license plates are possible with the new plate.
Now, of course, that doesn't take into account all the license plates that spell bad words. So it's not exactly accurate. There are a bunch that are taken off and not allowed to be used. I'm sure you could think of some that don't get used. All right, let's do some bank account hacking here. For an online bank account, the minimum security standards require a password to have 2 letters followed by 5 digits. So let's write those down. 2 letters followed by 5 digits. 1, 2, 3, 4, 5. So that's a letter, a digit, 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 digit. All right, letters. Now, does it say all letters and digits may be used more than once? Okay. Well, then that tells us that we've got 26 letters possible for the first one. And in the second one, we can repeat it. So we've got 26 again. Then the digits. We get to repeat all those. So that gives us 10, 10, 10, 10, and 10. Multiply those up, and we come up with 67,600,000. Now, often we're going to have times when repetition is not allowed. So if you're able to repeat your digits or your letters, the numbers stay the same. We could have also written this as 26 squared times 10 to the 5. That gives us the same answer. And that's explained here on the next page. Total number of choices may decrease if repetition is not allowed. For example, determine how many 3-digit numbers can be formed using 7, 8, and 9. Well, if repetition is allowed, then we've got 3 choices for every single digit. Or, in other words, 3 times 3 times 3. And that gives us 27. But if repetition is not allowed, the first one has 3 ways. The second one has 2 ways. And the third one, there's only 1 way left, 1 number. And that gives us 3 times 2 times 1, which is 6. The way that I'm always going to recommend it is draw out your lines. The first one gives you 3. We've used 1 up. That means in the second digit, I've only got 2 options to choose from because 1 was used. Now that I've used 2 of them, well, the last one has got to be that one last leftover digit. All right, so your last 2 questions there. What is the fundamental counting principle? And then how you decide if you're using a graphic organizer. That's something like a table or an array or a tree diagram, one of those types of things, or if you're going to use the fundamental counting principle.